Hello students, welcome to Engineers Academy. Now we are going to solve this problem from Hibbeler Dynamics. The problem says that rod OA rotates counterclockwise with a constant angular velocity theta dot equals to 5 radian per second. The double collar B is pin connected together such that one collar slides over the rotating rod and the other slides over the horizontal curved rod, of which the shape is described by the equation r equals to 1.52 minus cos of theta. So the shape of this curved rod is defined by this equation. R is a function of theta, and it is said that if both collars weigh 0.75 pounds, determine the normal force which the curved rod exerts on one collar at the instant when theta equals to 120 degree, and it is said that neglect friction. So now we are going to solve this problem by using the cylindrical coordinates, since we are given the shape of this as a function of r and theta. So we are going to solve this particular problem by using the cylindrical coordinates. So for that we will define our radial and theta direction. So in the outward direction this will be our radial direction, and the perpendicular direction in the direction of the increasing theta, that will be our theta direction, that will be our theta axis. So this is my theta axis, and this theta axis is perpendicular with the radial axis. If these two collars are moving around this circular arc, so let's assume that there is some acceleration in the positive radial direction. So let's say that that acceleration is AR, and similarly in the positive theta direction we have A theta, and out of the screen is the Z direction, since we are considering the cylindrical coordinates way. So we have R, theta and Z axis. So the Z axis is out of the screen, and since in the problem statement it is said that the mechanism is rotating in the horizontal plane. So this rod is horizontal, right? So this means that if we consider this mechanism as a horizontal, so then the weight is acting in the negative Z direction. If the positive Z direction is out of the screen, so the weight is acting inwards towards the screen. Now we are asked to find the normal force which the curved rod exerts on one collar when this theta is 120 degrees. So we have to find the normal force which this curved rod applies on this collar. So before that we have to find this AR and theta. So once we know this AR and theta, then we will be able to find the equation of motion to find that normal force which this curved rod is applying on this collar. So as we have these two equations, so this is the equation for AR from the kinematics, and this is E theta. So we are given that theta dot is the radial velocity, is the angular velocity is 5 radian per second, and it is said that it is the rod OA is rotating with constant angular velocity. So this means that theta double dot, the angular acceleration is 0. So theta double dot is the angular acceleration. Similarly, we are given r is a function of theta, so I will write r is 1.5 into 2 minus cos of theta, or we can write it is 1.5 into 2, so this is 3 minus, we can write it is 3 minus 1.5 cos of theta. Now if I take the derivative of this, so we will get the derivative of r with respect to time. So we will get this is r dot, and the derivative of 3 with respect to time is 0, and we will write minus, this will be 1.5, and the derivative of cos of theta is minus sine of theta, and then we have to apply the chain rule. We have to take the derivative of this theta with respect to t, with respect to time, so this will become theta dot. So this will become minus into minus, this will become plus. So r dot is plus 1.5 theta dot sine of theta. So this is r dot. Similarly, in these two equations, we also require r double dot. So I will take one another derivative with respect to time. So this will be 1.5, and then we have to apply the chain rule, right? So we will have to apply the product rule and the chain rule simultaneously, right? So this is theta dot, and then when we take the derivative of sine of theta, so this is cos of theta, and then one another derivative of theta, so that will become theta dot, and then I will write sine of theta, and then the derivative of theta dot, so that will become theta double dot. So this will become, if I multiply this theta dot with theta dot, so this will become theta dot square. So now we have this derivative. So now this is, now when this theta is 120 degrees, we want to find this AR, the radial acceleration, and the acceleration in the positive theta direction. So we have to find this r double dot theta dot at theta equals to 120 degrees. So now if I put theta equals to 120 degree in this equation, so I will find it directly. So this r equation is 3 minus 1.5 cos of theta, so I will write 3 minus 1.5 cos of 120 degrees. So this gives me 3.75. So this radius at theta equals to 120 degree is 3.75 feet. 3.75 feet. Similarly, if I put the values in this equation, so this is 1.5 and theta dot is 5 radian per second. So this is 5 and sine of 120 degrees. So this will give us our dot. So 1.5 into 5 sine of 120. And this gives us r dot equals to 6.495. Let me write that r dot here. That r dot is 6.495, and this is feet per second. Similarly, we can find our double dot. We can put the values in this equation. So again, theta dot is 5 and theta double dot is 0. So this whole term will become 0. So we will be left with this. So our double dot is 1.5 into theta dot square, so 5 square cos of 120 degrees. So our double dot is minus 18.75. So our double dot is minus 18.75. Now we can find this AR using this equation. So AR is r double dot, so r double dot is minus 18.75 minus r into theta dot square. So r is 3.75 when theta is 120 degrees into theta dot. So theta dot is 5, so this is 5 square. So now we can find that AR minus 18.75 minus 3.75 into 5 square. So AR comes out to be minus 112.5. So let me write that AR here. So AR equals to minus 112.5, and this is feet per second square. This is also feet. Similarly, we can find a theta. We can put the values. So R, when theta is 120 degrees, R is 3.75. So I will write 3.75 into theta double dot. Again, theta double dot is 0. So this will become 0. So we will be left with this term. So this is 2 times r dot, and r dot is 6.495 into theta dot, and theta dot is 5. So I will multiply it with 5. So this is 2 into 6.495 multiplied by 5. This gives me 64.95. 64.95 feet per second square. So this is a theta. Now we know the acceleration value in the theta direction and we know the acceleration value in the radial direction. So the negative sign means that the acceleration is acting inward. Now since we need to find the normal force which this curved arm applies on this collar, so we have to represent that force, and that normal force will be acting perpendicular to the tangent to this particular point, to this curved arm. So let me draw that tangent line. So the tangent, this green line is the tangent line at this particular point to this curved arm, right? This is that tangent, this green one is that tangent. Let me write that this is tangent. So the normal force which this curved arm will apply on this collar, so that normal force will be perpendicular to this tangent. So always that normal force will be perpendicular to this tangent line, right? Let's say that this is the normal force applied on the collar by the arm. And similarly, if this OA arm is moving in the counterclockwise direction, so there is a force on this OA arm. So that force will be acting along this theta direction, right? So let me draw that force. So this is that force. At any instant, the angle between the tangent and the radial direction, that angle will be represented by psi. And as we know that from theory, that psi is equal to tan psi is equal to r divided by dr by d theta. So now if we want to find the psi, so we can find the r value at theta equals to 120 degree, and we have to find dr by d theta. So since r is, we are given that r is equal to this 3 minus 1.5 cos of theta, 3 minus 1.5 cos of theta. So this r dot is the derivative of r with respect to t. Now we have to take the derivative of this r with respect to theta. So this is again 0 and this is minus 1.5, and the derivative of cos of theta with respect to theta is sine of theta, and that will be minus sine of theta, so that will become plus. And since this theta is this cos is a function of theta, so there is no need to apply the chain rule, right? So this is the derivative of this r with respect to theta. So now we can find this dr by d theta value at angle theta equals to 120 degrees. So we can write that this is 1.5 sine of 120 degrees. So 1.5 sine of 120 degrees. So this gives us 1.299, 1.299. So now we can find this psi. So I can write that this psi will be equal to tan inverse of this ratio. So we can find it directly. Now we can write that tan inverse r, so r value is 3.75 when theta is 120 degrees, and dr by d theta is 1.299 when theta is equal to 120 degrees. So that psi comes out to be 70.89. So psi angle equals to 70.894 degrees. And since we get this sine is positive, so this means that, and this is that psi angle, and this psi angle is measured in the counterclockwise direction from that r. So now this psi is 70.894 degrees. Now if this angle is psi, then this angle is also psi, and again that psi angle is measured in the counterclockwise direction, so this is that psi angle as well. So this is psi. And now as we know that this NC force is perpendicular to this tangent, this will always be perpendicular to that tangent. So this whole angle is 90 degrees. So if this NC is making some angle with the radial direction, so let's say that that angle is phi. So we can find this phi. We can write that psi plus phi, this is equal to 90 degrees. So we can find the angle of the NC with the r axis is, that will be equal to 90 minus psi. So we can find it. Psi is 70.894. So 90 minus 70.894. This gives me 19.106. So phi is 19.106. So now we know the angle of NC with the radial axis. Now let me erase all these. And we know the angle of NC, that is phi angle. Let me write it here. So this is that force which is applied on this collar due to this OA arm, and we have to find this NC. So we can resolve this NC into its components along the radial and theta direction. So if I resolve this NC force into its components, so we will have two components. One of its component will be acting in this direction, and one of its component will be acting in this direction, that is in the positive theta direction. So this one is the cos component. I can write that this is NC cos of phi, and similarly this component is NC sin of phi. So now if we apply the summation of forces along the radial axis is equals to MAR. So as we can see that in the radial direction we have this cos component of NC. So and it is acting in the negative radial direction. So I will write minus NC cos of phi, and we know phi is 19.106 degrees. So this is 19.106 degrees, and this will be equal to the mass. So the weight is 0.75. So the mass will be 0.75 divided by G value, which is 32.2 feet per second square, into AR. And we know that AR value, which is minus 112.5. So from this we can find and see, if we divide both sides of the equation by minus cos of 19.106, so we will be left with NC. So NC, we can find it directly using calculator. So this is 0.75 into minus 112.5 divided by 32.2 into minus cos of 19.106. So this gives me NC equals to 2.773 pounds. And similarly we can find this F value, that the force that applies, this OA arm applies on this collar. So we can apply that, we can find that if we apply the summation of forces along the theta direction, and this will be equal to MA theta. And as we can see that in the positive theta direction we have this F force, or let me write that this is FOA force. So I can write this is FOA plus that sine component of NC. Now we know NC is 2.773 sine of phi, and we know phi as well, which is 19.106, and this is equal to mass. So the mass is 0, the weight is 0.5 divided by 32.2 multiplied by this A theta. So A theta is 64.95. So this is 64.95. So now we can find it. So we can write it as FOA will be equal to this thing minus this term, right? So I will do it directly in calculator. So we can write that this is 0.75 into 64.95 divided by 32.2 minus the sine component of NC, which is 2.773 sine of 19.106. So this gives me FOA, the force applied by the OA arm on the collar, equals to 0.605 pounds. So this is the solution of this particular problem. Kindly subscribe my channel if it helps in your learning. Also like this video if you people want me to solve such more problems from Hibbeler Dynamics.